Look at the Earth from space. It is a massive sphere covered by millions of square miles of ocean, broken up by 7 distinct landmasses we call continents. But trying to study or navigate something this large presents an immediate physical problem. If you're standing on the surface, there are no natural grid lines or markers to tell you exactly where you are relative to everything else. To solve this, humanity built the globe. A physical desktop globe provides a true-to-life, 3-dimensional miniature model of the Earth. It accurately captures the shape and the relative positions of those oceans and continents. But carrying a bronze-stand sphere in your pocket while walking through a city isn't practical. Plus, a globe only provides a zoomed-out, macro-level view of the planet. To track broad climate patterns and also find the quickest route to the local bank, we had to invent a universal geographic language. We needed to wrap the Earth in an invisible mathematical grid. That grid starts with a single horizontal line. The equator wraps around the widest part of the planet and slices it perfectly in half, dividing the Earth into the northern and southern hemispheres. Next, we need a vertical divider. This sign at the Greenwich Observatory in London marks the prime meridian. It operates as the starting vertical line that drops straight from the North Pole to the South Pole, separating the eastern and western hemispheres. This diagram shows horizontal rings, like the Tropic of Cancer, marking our global heat zones, the torrid, temperate, and frigid zones. Finally, intersecting vertical longitudes, or meridians, create exact mathematical coordinates. This complete invisible grid allows us to mathematically pinpoint any location on the planet and predict its environment before we ever arrive. Since we can't carry globes everywhere, we have to flatten this 3D sphere onto a 2-dimensional piece of paper. Taking the skin off a sphere and laying it flat always stretches and distorts the shapes of the landmasses. While geometric distortion is an unavoidable compromise of paper maps, mapmakers solve the separate problem of visual clutter by categorizing data. Physical maps, for example, ignore human borders to focus strictly on natural terrain like mountains, deserts, and rivers. Political maps clear away the topography to focus on human-made boundaries. Here, the lines define exactly where one country or state ends and another begins. Then there are thematic maps. These strip away almost all general geography to isolate a single dataset, like mapping out locations of national parks or tracking average annual rainfall. Moving from 3D to 2D requires us to accept a distorted view of the planet, but specializing maps into physical, political, and thematic types ensures that the specific data we need remains clear and legible. When we zoom all the way down to a single city street, a new physical challenge immediately emerges: figuring out how to fit miles of real-world roads and buildings onto a small piece of paper. The solution is the map scale. By using a strict mathematical ratio, a single centimeter drawn on a page can represent 500 meters of actual pavement on the ground. Look closely at this antique chart. The multi-pointed compass rose establishes a fixed orientation, locking north, south, east, and west so you can properly align the paper with the physical world. Finally, rather than trying to draw complex, miniature versions of actual buildings, maps use standardized symbols. A simple blue line stands in for a winding river, and a cross clearly marks a hospital. Scale, direction, and symbols operate as the map's underlying code. They compress massive, cluttered physical environments into a readable, pocket-sized format. When you pull back from that single street level, up through the atmospheric layers to our view in orbit, the entire system connects. Those lines of latitude and longitude, the map scales, and the standardized symbols operate as a cohesive, universal language shared across the globe. It is a framework that scales perfectly. The exact same coordinate system that plots a cargo ship's voyage across the Pacific Ocean is used to map the quickest walking route to your local grocery store. By layering this mathematical grid over our world and shrinking it down to scale, we took a massive, unchartable sphere floating in space and turned it into a measurable, fully navigable home.